So in this lecture, we're gonna study about stream functions and velocity potential. We've had a basic glimpse of stream function in previous lectures, but we're gonna use these two scalar representations of the velocity field for describing ideal flows. Now, ideal flows are something which are not suffering from non-idealities such as viscosity. And you may feel like every flow that exists must have a certain degree of non-ideality inbuilt, and that's absolutely correct. But the point is to understand that there are zones in the flow where the non-idealities are not that important. Let us consider the flow over an aircraft wing. So this is the cross section of an aircraft wing. So there is some flow like this. So the effect of viscosity is to tell this particular incipient flow that yes, there is some effect of the no slip boundary condition at the surface of the wing. So at the surface of the wing, u will be equal to 0 locally, and actually v also will be equal to 0 by no penetration boundary condition. So effectively at a solid boundary, the velocity is 0, and this is a consequence of no slip and no penetration. Well, no slip boundary condition is a consequence of the presence of viscosity. If viscosity were to be absent, there would be no physical mechanism for the velocity disturbance, that is the presence of this wing, to propagate into the fluid. So imagine this is a flat plate, there is some incoming flow like this. So because of this solid wall, which is at a 0 velocity, the very first layer will start to feel the effect of the wall. But the other layers are sort of oblivious to the presence of the wall and they will continue. So it will be something like this. Then as you go further, the disturbance will propagate inwards, rather outwards. And the propagation of this disturbance is governed by viscosity. In fact, the time taken for viscosity to sort of diffuse over a distance L is L square upon mu, where nu is the kinematic viscosity, and it is defined as the ratio of the dynamic viscosity upon the density. So you can verify the units. L square has the units of meter square, while nu has a units of meter square per second. So after this much amount of time, the disturbance, that is velocity equal to 0, that disturbance would have propagated a distance equal to L, and after this much time the velocity would have traveled by the average velocity times the time. This is the distance in this direction. So there is a boundary layer. So this growth is governed like this. So further you go, the larger the momentum is diffusing upwards, and inside this region viscosity is important. Outside this range, the flow has not yet felt the influence of the wall, meaning that the disturbance has not yet propagated that particular distance. It has not gone beyond this. So this boundary inside which the viscous effects are important is called as the boundary layer. Outside it is independent. So for the flow over a wing, inverted wing. So for the flow over the wing, there is a region very close to the wing where the viscous effects are important, and outside, in the outside regions, the viscous effects are not important. So if the incipient flow is constant density and irrotational, then we can make use of the inviscid equations. So the equations are the continuity equations, and in general we have the entire governing equation as rho du dt is equal to minus grad p plus mu nabla square u plus rho g. But we have seen that we can express this particular term in terms of vorticity. So mu nabla square u, because uh, there's three vectors in here, two gradient vectors and one velocity vector. We can express it in terms of the gradient of divergence of u and the curl of the velocity, the vorticity. So we can express this in terms of the curl of the vorticity. Let me just dig up the expression real quick. Yeah. So the expression is this is equal to minus curl of the vorticity, where we have already made use of the continuity equation. The fact that the flow is incompressible. This makes use of the fact that the flow is incompressible. So if the incipient flow lacks vorticity, then this particular term also vanishes, because the viscous term will vanish if the vorticity is 0. So only in the vicinity of the wall this entire equation would be valid, but away from the wall, because the viscous effects have not yet come into picture, the governing equations would be this. Note that we have not explicitly said that the flow is, rather the fluid is inviscid. We have nowhere said that. We have only made use of the fact that if the outer flow is rotation free, then the effect of viscosity anyway does not manifest itself. So you have, so suppose you take a box and there is a conveyor belt, right? If the conveyor belt is absolutely smooth, even when you drop this box, there will be no friction to hold on to this, and there will, regardless of the normal force, there will be no mu, that is the coefficient of static friction. So mu n would be 0, so this box would not actually move with the conveyor belt. It's something like that. It is because of the static friction that the box will start to move with the conveyor belt. Okay, so if you take a stick and then you drop it to on top of a moving conveyor belt, the stick will be imparted a net rotation, because the lower part will start to rotate like this while the upper part is still stationary, and the upper part will appear to rotate like this. So it is only viscosity that is able to make an originally irrotational flow rotational. If there is no viscosity, an irrotational flow forever remains irrotational. So without the influence of viscosity, an original, pardon me. So an original irrotational flow remains irrotational, and this is a consequence of Kelvin's vorticity theorem. and we have not studied this in this preliminary course. You can look it up if you're interested. So far we've understood that there are zones where viscosity is important, there are zones where viscosity is not important. In fact, if those zones where viscosity is not important, if they are uh, free of vorticity and their constant density flows, then we can make use of certain special representations. So the first representation is by the is with the help of the continuity equation. Actually, before moving to that, I just want to give you a quick overview of what really happens. And it was the theoretical insight of von Karman, who was a great engineer, and actually he laid the foundations of a very important field of applied mathematics as well. So if the viscous effects are very important close to the wall, you eventually have to match the condition at the edge of the boundary layer with the conditions outside. So the conditions outside are as if everything is inviscid, but the conditions inside the boundary layer appear to be viscous. Moreover, if the conditions inside are viscous and they are confined to a very small boundary, if you are interested in only the flow characteristics of the outer flow, the inviscid flow is enough to tell you how the streamlines would look. However, to find out properties like the drag or the lift acting on the wing, it is very important for us to resolve the entire dynamics happening inside the boundary layer. And in fact, most of the explanations why aircrafts experience lift, which make use of the Bernoulli theorem, they are absolutely incorrect. In fact, an aircraft would not experience any lift had there be no viscosity. So the presence of viscosity leads to the development of a viscous boundary layer, which leads to the generation of stress, and the stress differential between the top and the bottom surfaces is essentially responsible for the generation of lift and drag. Now, if you want to analyze the flow outside, you can do it without alluring much to viscosity, but there are certain issues that come into picture. Consider the Gurney equations once again. On the right hand side, in one equation, we had mu nabla square u vector, and in the other equation this term did not appear, but this equation is second order in velocity, meaning we need two boundary conditions to satisfy this. The first boundary condition comes from the no slip boundary condition, and the second one can be no penetration. Whereas for the inviscid flow, there is only there the whole equation is only first order. It is only first order because of this term, and as a consequence of this, you cannot enforce two boundary conditions. You cannot enforce the no slip boundary condition on an inviscid flow. The best you can do is to enforce no penetration boundary condition into a solid boundary. That's the best you can do. Okay, so more on the boundary layers later, but for now, let us look at simplifications of the velocity fields in 2D with the help of stream functions and velocity potential. So consider an incompressible 2D flow. So an incompressible 2D flow is given by del u del x plus del v del y equal to 0. Now, if this is true, we can represent the velocity components in terms of a single scalar psi. So psi, which is also called as the stream function, can be used to represent the components of the velocity. So the u component of velocity can be written as del psi del y, while the v component of velocity can be written as minus del psi del x. So psi is a function of x and y. Now, If this is true, let us write down what happens when we reside on a iso psi line, on a line which is having a constant value of psi. So d psi on that particular line will be equal to 0, and d psi by definition is del psi del x dx plus del psi del y dy, and del psi del x is minus v and del psi del y is plus u, and this is equal to 0. Therefore v dx equal to u dy, and which implies dy by dx for psi equal to constant line is equal to v upon u. And if you recall, dy dx being equal to v upon u is tantamount to the definition of a streamline. So the stream function, wherever stream function is constant, if this is a constant stream function line, then it is also a streamline. But just because a certain line is a streamline does not imply, it does not imply that that line is a constant stream function line. It does not imply. And the reason is clear. For the definition of streamline to be valid, it is sufficient to find out this. It is sufficient to find out this. Nowhere does it require the flow to be incompressible. This particular condition does not require the flow to be incompressible. But if you start off with the assumption that the flow is incompressible, then a constant stream function line will also be a streamline. So now let us proceed and write down the expression for the vorticity in terms of the stream function. So the vorticity for two-dimensional flows, only the z component of vorticity will be non-zero, and that will be del v del x minus del u del y. And recall that u equal to del psi del x del y and v equal to minus del psi del x. So the first term del v del x is essentially minus del 2 psi del x2, and this particular term becomes minus del 2 psi del y2. So the vorticity is essentially minus Laplacian of psi. But we are working under the premise that the overall flow outside the regions of appreciable viscosity, they are irrotational. Okay, if they are irrotational, then the effects of viscosity are not important. But additionally, we can have, so if this is the domain overall can be irrotational, but we can have singular points where the vorticity can be non-zero. So there can be points of irrotational vortices. There can be points of irrotational vortices. And one example of an irrotational vortex is, we had done this when we had studied fluid kinematics. So that is called as, not called as, but we can define it as ur equal to 0 and u theta equal to b upon r. So this particular flow specification has, so suppose this is the origin. So only if you consider a contour which encompasses the origin, then the vorticity is 0, but at all the other points, it is 0. The vorticity is 0, and at the origin the vorticity becomes infinite. So it is like a singular point which imparts vorticity to the flow. So in order to accommodate the presence of such singular points, we can write down this particular expression in terms of a Dirac delta function. So we can write minus Laplacian of psi is equal to gamma times delta of x minus x prime delta of y minus y prime. So the Dirac delta function is used to pinpoint the location of such a vortex. So what is the Dirac delta function? So Dirac delta function is a function, so delta x minus x prime, it will be infinite at x prime equal to x, or rather x equal to x prime, and it will be 0 everywhere. And the property of a Dirac delta function is integral f of x delta x minus x prime dx for a domain which contains x prime. So this is the integration domain and x prime lies inside the domain. So this will be equal to fx prime, and if the point lies outside the domain of integration, it will be 0. So the important property is it is a selector, that wherever you want the evaluation of the function, you multiply it by the Dirac delta function at that point, and then you integrate it over the entire domain, and you will select the value of the function at that desired point. So Dirac delta function is used to select or identify a point loading. And Dirac delta function has a lot of use in Green's functions for solving ODEs and PDEs. You can represent a continuous function as a discrete function at various points in the domain. Okay, so it's almost like you have a string and you are pinching the string at a few points. So it's like Dirac delta function at this point and Dirac delta function at this point. But for now, you don't have to worry a lot. It's sufficient to know that the Laplacian of psi is minus gamma delta x minus x prime delta y minus y prime, and the important property of a Dirac delta function in 2 dimensions is that if you integrate the Dirac delta function, if you integrate the Dirac delta function over this entire space, you will obtain 1. I mean, here if it's gamma, then you will obtain gamma, given that the space is encompassing this particular x prime y prime point. Okay, so finally the useful equations that we have are this everywhere and this in order to accommodate point vortices, irrotational vortices. So what is the solution of this particular equation? Well, you cannot just straight away tell me the solution of this particular equations because I have not told you the boundary conditions. But regardless of that, if we assume far stream boundary conditions, and you'll understand what I mean by far stream boundary conditions in a moment. Let us consider this solution, psi equal to minus Vx plus Uy. So what is the U component of velocity? It is del psi by del y and it is capital U. What is the V component of velocity? It is minus del psi by del x and it is capital V. So this particular stream function is responsible for a uniform flow. Meaning that at whatever location you are in the domain, you will be obtaining a velocity capital U and capital V. Now let us turn our attention to this slightly annoying thing. Now you may not be experienced to tackle this at this particular moment, but I'll show you a very easy way of doing it. So now so this is the equation. Suppose this is the point of singularity. Suppose I choose x prime and y prime to be at the origin. Now I want to this is the space where everything is going on, then this is the origin. So I can integrate this equation over this entire space, right? So this Laplacian need not be written in Cartesian form itself. I can choose not to write this Laplacian in a Cartesian form. I can choose it, I can choose to write it in a cylindrical polar coordinate system. And because the Dirac delta function does not have any directional dependency, I can choose only to write the r dependency of this function. The Dirac delta function is a point singularity and it does not have that dependency. You can simply write it in terms of, uh, you can simply choose to write it in terms of r and not theta. So now what about this other term? So let me integrate this. So integration of this over the area is integration of this times 2 pi r dr. Okay, and is equal to minus gamma integration delta x minus x prime delta y minus y prime dA, and so this will turn out to be minus gamma. So it's just I'm not writing dA in terms of r. Okay, it's simply going to be minus gamma. So this r gets cancelled, this 2 pi can be taken over here, so essentially it's ddr of r del psi del r dr is equal to minus gamma by 2 pi. So this is going to be r del psi by del r over the boundary, over this boundary, okay, and this is going to be minus gamma by 2 pi. So minus rather del psi del r is equal to minus gamma by 2 pi r for all points on the boundary, and the boundary can be arbitrarily shrunk. All I need to do is to not shrink it to 0, but I can shrink the boundary wherever I want. I can choose, so this r wherever it is, I can choose that r, but I don't want to make it 0. So integrating this, I can simply write r, rather psi equal to minus gamma by 2 pi ln r. This dr goes over here, I can integrate it. Constant of integration I can choose to be 0 because the velocities are not dependent on the absolute value of psi, but rather on the gradients of psi. So I can choose the constant to be 0. So this solution is called as a fundamental solution. And this solution is called a fundamental solution because it tells me the stream function, the nature of the stream function at the point where there is a irrotational vortex. So at all the points the vorticity is 0, at this point vorticity is infinite, and it gives a circulation equal to gamma. So from this point I can sort of estimate what this function is going to be. And remember that all the equations that govern psi are linear. So because these are linear equations, I can sort of add as many disturbances I want to this flow. All the disturbance, all the solutions found out individually can be superposed, and that is possible because these equations are linear in nature. Similarly, I can find a variety of solutions for this, and then I can simply add those solutions to find a grander solution. It's a property of a linear equation. So far we've found out a very simple solution for a uniform flow. We'll find out more solutions. So for a uniform flow, psi is equal to minus uh, Vx plus Uy. For an irrotational vortex, point vortex, psi, the fundamental solution is minus gamma by 2 pi ln r. Okay, so these are some basic solutions, and in fact I had shifted the coordinate system locally to 0. I had shifted it to 0, so I can shift it back, and when I shift it back it's simply going to be 2 pi ln, so square root of x minus x prime whole square plus y minus y prime whole square, where the disturbance is acting at the location x prime y prime. So it's just shifting it back. And this coordinate transform is nothing confusing. It's just that you are writing down The solution, instead of writing it down at the origin, you are now writing it down at x prime, y prime, where that singularity is now acting. Now, we've started off with an incompressible uh, flow, and we have made use of all the tools that we have, irrotational flow and all that, to find out this set of equations. Alternately, we can also start off with a irrotational flow and make use of the mass continuity or the incompressibility equation to find out what we obtain. So an irrotational flow, omega z is 0 and it is equal to del v del x minus del u del y. If this is the nature of the flow, if it is equal to 0, then the flow can again be represented in terms of phi, where phi is called as the velocity potential. Phi is called as the velocity potential, and the u component of velocity is simply del phi del x, and the v component of velocity is simply del phi del y. And this is simply tantamount to writing u vector is gradient of phi. And this should be obvious because the omega z is nothing but the rather the k component. So the omega vector is simply the curl of the velocity. So curl of velocity being equal to 0 vector implies that the velocity field can be written as the gradient of a scalar, and that particular scalar is nothing but the velocity potential. With this, we can now make use of this particular set of relationships to write down the the incompressibility condition. So when the flow domain is everywhere incompressible, we can write this equal to 0. So what is this? So it's del u del x plus del v del y, and u is equal to del phi del x. So this becomes del 2 phi del x2 plus del 2 phi del y2, and this becomes equal to Laplacian of phi. And it is 0 for all the points in the domain except, so it is 0 for all x in domain except where there are there are point sinks or point masses coming in or coming out. So point sources. So it's going to be equal to m times delta x minus x prime delta y minus y prime. So imagine this entire domain where mass conservation is true everywhere, but there can be some points where mass is sort of entering into the domain, okay, and there can be some points where mass is leaving the domain. So except these points, everywhere it is incompressible, but these points, if you encompass these points, you have a mass source. This is a mass source, or you can alternately have, if you encompass that point, you have a mass sink. If you take any other area, it has to conserve mass. There is no sink or source of mass. So that is why we can write down, just like we had written down for the case of irrotational vortex, we can write down this expression. And so the basic equations are this equal to 0 and this equal to m delta x minus x prime delta y minus y prime. And similarly, if you want to write down the solution for a uniform flow, from here you can write phi is equal to ux plus vy. You can check it. So u is equal to del phi del x, and that comes out to be capital U, and v comes out to be del phi del y, and that comes out to be capital V. And so this is in fact the velocity potential for a uniform flow. Similarly, you can write down the fundamental solution, and just as a side note, this fundamental solution is actually also the Green's solution. It's also the Green's solution, So phi for this particular equation, which is the equation which is sort of forced. It is a Laplacian equation which is forced by a point mass source or a point mass sink. Try to appreciate that this is a equation which is forced by a point mass source or a mass sink, and this will be equal to m upon 2 pi ln of square root of x minus x prime whole square plus y minus y prime whole square. And if you want to write it down in terms of a coordinate system which is shifted at the origin, then you can write it down as m upon 2 pi ln r, nothing else. Everything else remains the same.